All right, so we are getting into the ending of our unit. All right, just got like 2 little topics left to do. So this is chapter 7. We're calling it our unit 1 because it's our first unit of new material. And we are doing section 7.8a, and then we're also going to do 7.8b. So I'm splitting it up into 2 little topics instead of doing it all in one. So this first one's called improper integrals. We've never evaluated an improper integral before. All right, so we've never done an integral and how to do an antiderivative of something that is improper. So we need to talk about what that means too. All right, and the first type of improper integral we're going to look at is called an infinite interval. That means we're integrating something over an interval that is infinite. Okay? So our outcome is I can determine if an improper integral of infinite interval, say that 10 times fast, converges or diverges. Okay, quit trying to say it 10 times. All right, I can determine if an improper integral of infinite interval converges or diverges. And we need to also talk about what converging and diverging means. All right, so let's take a look at this. First of all, what is an improper integral of infinite interval? All right, so we know how to evaluate a definite integral like this, right? We know how to integrate from 1 to 3, 2x dx. That's going to be the antiderivative x squared. And we know we're doing from 1 to 3. So then we're going to do the fundamental theorem, and we're going to get 3 squared minus 1 squared, which would be 9 minus 1, which is 8. Okay? So what about this integral down here? What if I wanted to evaluate the integral from 1 to infinity of 2x dx? This is called an improper integral because it has an infinite interval from 1 to infinity. We have an infinite interval. So that's what an improper integral is. That's one type, infinite interval. So we're going to look at how do we deal with an infinite interval. Well, we are going to rewrite, and let's take a look at this just a minute here, because this is 3 different things. This is one thing here, this is one thing here, and this is a third thing down here. So this is 3 different things. So don't think that was all mashed up as one big thing, like, oh my goodness, I'm going to do all that. No. All right, the first thing up here. We're talking about improper integrals, and the first type of improper integral we're talking about is one that's an infinite interval. All right, so this is an example of an infinite interval. We're integrating from a to infinity for some function. So what we're going to do is we're going to replace the infinity with a t, and then we're going to say, let's take the limit of this integral as the t goes to infinity. So we replace the infinity with a t, and then we're going to put the limit and let t go to infinity. So we're rewriting it, and then we're going to work it out that way. You can also do an integral that has a negative infinity as a. So it's the same idea. You replace the negative infinity with a t, and you're going to take the limit as t goes to negative infinity. All right, so we're going to rewrite the problem. Now, what if we have a problem? This is a third kind. What if we have a problem that has infinities on both ends of our intervals? We got a majorly infinite interval, right? No kidding. We're going from negative infinity to positive infinity, so we got issues on both ends. So what you do is this is the one where you pick a number in between, all right? And you can pick anything you want in between. I usually pick 0 to make it easy. That's usually 0 or 1 or something that's really simple. So you're going to pick any number you want. Typically it's 0 or 1, something simple. And we're going to break up this interval. We're going to say from negative infinity to a, say negative infinity to 0. And then we're going to do another integral going from a to infinity. And if you chose 0, you would do 0 to infinity. So you're breaking it up into 2 parts. And then you probably figured out from there, you're going to take the limit of each one and combine the first 2 types up here together. So for the first half, we're going to replace the infinity here with a t, and we're going to do let t go to negative infinity. Sorry, we're going to place the negative infinity with t. And then for the second one, we're going to replace the infinity with a t, and then we're going to let t go to positive infinity on that one. So you're basically doing these first two together because we have both ends being an infinite amount, okay? So you split it into two of them and do two different limits. And then we're going to work out both parts. We're going to do the antiderivative, do the integral, take the limit, do all of that business, right? So instead of making two videos, we're just going to keep on going on this one. All right, so our last thing is we talked about in the outcome for the day, what does convergent and divergent mean? Well, it basically means you get an answer or you don't. All right, convergent means your limit exists and you get an actual finite answer. Divergent means your limit doesn't exist, so we're getting like infinity or negative infinity for our answer. All right, so here's two examples. The integral from 1 to infinity of 1 over x squared dx, if we were to work that one out, it converges. And then this one is an example of a divergent one, which I know we're going to work that one out. Okay, and we're going to talk about this one too at some point. All right, so this one we're going to work out. That's going to be actually our first example. This one is the integral from 1 to infinity of 1 over x dx, and we're going to find out that that one diverges. Okay, so diverges means the answer is not a finite number. You get like infinity or negative infinity. All right, so let's just see how are we going to go about this. So instead of doing two different videos, I'm just going to keep on going because this won't be very, very long, I don't think, altogether. All right, determine whether the integral is convergent or divergent. So that just means you get an answer or do you not? Okay, does your answer exist or does it not exist? Okay, so the first thing we're going to do is we're going to rewrite this limit because it has an infinite interval. So we're going to rewrite it as the limit as t goes to infinity of the integral from 1 to t of 1 over x dx. So the first thing we're doing is replacing the infinity symbol with a t, and then we're going to take the limit and let t go to infinity. So that's the first thing we're going to do. All right. Now, after that, you're actually going to do your antiderivative. So we're doing the limit as t goes to infinity of the integral. Well, I won't leave the integral if I'm taking the antiderivative. All right, I'm going to do the antiderivative, and then I'm going to be evaluating from 1 to t. So let's figure out what the antiderivative of 1 over x is. Well, you should be shouting in your brain right now to me what the antiderivative of 1 over x is. That is natural log of the absolute value of x. All right, that's the antiderivative of 1 over x is natural log, right? So now we're going to do the fundamental theorem. So I'm going to do the limit as t goes to infinity. I'm going to do the fundamental theorem in here, right? So I'm going to do fundamental theorem of calculus, right? And the only reason I put the big brackets is because I got to take the limit of all this, okay? So I'm trying to keep it organized. So now we're going to put the t in first, so that would be natural log of t. And we're letting t go to infinity, so that's going to be a positive number, so I don't need brackets or anything. And then minus, putting a 1 in here is going to be the natural log of 1. All right, so now we're ready to simplify. All right, so we're doing the limit as t goes to infinity. What do we end up with when we simplify this? Well, we know the natural log of 1, that's 0. So this just ends up being ln of t. That's all it ends up being, natural log of t. So now we're ready to take the limit. So if you take the limit and let t go to infinity, what happens to the answer for the limit of infinity? So you have to think about what this looks like, right? Think about what the graph of ln looks like. It looks like this. Okay? That's what the natural log function looks like. So as t goes to infinity, so what happens as t goes to infinity? What's happening to your y-coordinate here? It's going to keep going up and up forever. So this answer is infinity, which means it does not exist. All right? Which means this function up here diverges. So diverges means we get an answer that does not exist. All right, so let's just recap what we did here. We were doing an integral from 1 to infinity. So the first thing we did was we replaced the infinity with a t, and then we're going to take the limit and let t go to infinity. So then you work it out just like normal. You do your antiderivative, you do the fundamental theorem, and once you're done with all that, then you take the limit and let t go to infinity and figure out what your answer is going to be. If you get an actual finite numerical answer, then the problem converges. Converges means you actually get an answer. Divergent means you get a does not exist. okay, which will be a positive or a negative infinity. All right, so that one we found out diverges. All right, so now let's look at this problem. All right, so for this problem, I've got the infinity in the a value. It's a negative infinity. So first thing I'm going to do, I'm going to take the limit and let t go to negative infinity. So I'm going to replace the negative infinity with a t. That's the first thing you do. So you're replacing the negative infinity with a t, and then we're doing the limit of this integral and letting t go to negative infinity. Okay? That's all you do is just setting it up. So now, at this point, we have to find the antiderivative. We have to find the antiderivative of x e to the x. All right? That's what we got to do. We got to find the antiderivative and then evaluate it from t to 0. So let's think about this a minute. We've got x e to the x. We've done this before. We just learned how to do it. This is one where we got to do ultraviolet voodoo. Okay? Now, you don't have to do the u and the dv. We can do the table thing. We can pick x to be our polynomial, right? And then e to the x to be the one we're going to do the antiderivative of. So I can do the tabular method. So I start with x. The derivative of x is 1, and then the derivative of 1 is 0. And then in this column, e to the x, well, e to the x, his antiderivative is e to the x. The antiderivative of that's e to the x. And remember, to find our antiderivative of this problem, we go diagonally, and we do keep change. So it's going to be x e to the x, and then minus an e to the x. So that's our antiderivative for this problem. All right, so x e to the x minus e to the x. That's our antiderivative. Okay, so what I did to find the antiderivative is what we already learned to do. Right, we learned how to do ultraviolet voodoo. Okay, and the tabular method is easy to use when one of your functions is a polynomial. And then the other thing is easy to do the antiderivative of. And then you do the keep, flip, change along the diagonals. Okay, you just always take whatever your polynomial is and keep taking its derivative until you get 0. And that's how many rows you have. Okay, all right, so now we're ready to keep going with this problem that we found the antiderivative of that. So now we go ahead and do the fundamental theorem. So my fundamental theorem, right? I'll try to get it to fit in here. I think I can. Fundamental theorem of calculus. So I'm going to put a 0 in here. So that's going to be 0 times e to the 0. Well, that's a no-brainer. Minus e to the 0. And then I'm going to subtract, putting a t in here. So t e to the t minus e to the t. All right. Well, we know this first one. This is 0, obviously. E to the 0, that's 1. So what have we got at this point? We have negative 1 minus t e to the t minus e to the t. So that's what we've got so far. So now we got to figure out what is the value of each one of these expressions as t goes to negative infinity. All right, well, the first one here is easy. The limit of a constant is a constant. So that part right there, the answer is negative 1. All right, the limit of a constant is that constant. All right, so I'm done there. All right, now I got to figure what happens with these two guys. Okay, this first one, well, I'm actually the last one's the easier one to do first. If you put a negative infinity in here, let me pull up so I got space. If you put negative infinity in here for this t, you're going to have an e to the negative infinity, which that can be written, be rewritten, because remember you're letting t go to negative infinity. So that can be written as 1 over e to the infinity. Okay? Now, I'm putting t goes to negative infinity. So if I put a negative infinity in here, I'm going to have e to the negative infinity. I can rewrite that since that's a negative power. I can throw it to the bottom. So that's going to be 1 over e to the infinity, which that's that's 1 divided by a really big number. So this is going to go to 0. 1 divided by a big number. So this is going to go to 0. So that's going to be minus 0. Now we got to figure out what's happening here on this part. Okay? When you put negative infinity in there. Well, we just did the e to the t part here when I did this part here on the end. So we know the e to the t part, that's going to be 0. And if I'm putting negative infinity in here, then I'm doing infinity times 0, and that's what we did earlier. That is an indeterminate product. Okay, so this is an indeterminate product here. So what we got to do is we got to rewrite that to figure out what the value is as we take the limit and let t go to negative infinity. So how do we fix an indeterminate product? We have to make it a quotient, right? We got to make it a quotient so we can do L'Hopital's rule if we need to. All right, so let's see if we can rewrite. Why don't I just throw this e to the t to the denominator? All right, so if I do negative t and put the e to the t in the denominator, that'll be e to the negative t. So I'm just going to rewrite it that way. What will be the limit or the value if we put negative infinity in here now? If I put negative infinity in here now, I'm going to have infinity over, now if I put negative infinity in here, I'm going to have positive infinity. So e to the positive infinity is infinity. So we're going to end up having infinity over infinity, which now allows me to do L'Hopital's rule. So what I'm trying to do is I'm trying to do the limit. I'm trying to do the limit and let t go to negative infinity. So when I do that with rewriting this indeterminate product, I threw the e to the t to the denominator. All right, so now I have negative t over e to the negative t. When you put negative infinity in here now, you get infinity over infinity, which now allows me to do L'Hopital's rule. Okay, so now, and you don't have to write all this out special. We just have to think through the. You'll memorize these probably as we go along. As we do enough of these, you'll know who goes to infinity, who does what. All right, so we're just doing scratch work to figure out what these three parts are doing. The first part's -1 so far. The last part here went to 0. The part in the middle was infinity times 0, so that was an indeterminate product. So I had to write it as a quotient, and now I'm trying to figure out what the answer is. All right, so now I got infinity over infinity. That means I can do L'Hopital's rule. So now I can do the derivative over the derivative. So when I take the derivative of negative t, I get -1. And when I take the derivative of e to the negative t, I get e to the negative t times -1. So now I do negative infinity again. All right, so when I plug in negative infinity in here, I'm going to end up with -1 in the numerator, but putting negative infinity in the denominator gives me e to the positive infinity, which is going to be a big number, infinity. So I have -1 divided by infinity, so this is going to go to 0. So this part goes to 0, that part goes to 0, so the answer is -1, so that means this problem converges to -1. All right? So what you have to do for every single problem is you have to rewrite it, and then you're going to do the fundamental theorem, and then you've got to figure out, as t goes to infinity or negative infinity, what the answers are. So sometimes it's going to involve doing an indeterminate product or an indeterminate quotient that we've already studied in the last section. All right, so that one was -1 and converged. All right, so now here's an example of one where you have infinity on both ends. Okay, and I'm even telling you, choose your a value to be 0, because that's typically what I choose all the time. So what I'm going to do is I'm going to split this up into negative infinity to the 0 of 1 over 1 plus x squared dx, plus the integral from 0 to infinity of 1 over 1 plus x squared dx. So I'm splitting this integral up, since it's got infinity on both ends. I'm going to split it up into 2 separate integrals, and I'm going to choose my splitting number as 0. That's where I'm going to split this interval, and now we're going to do each part individually. So on this one, I'm going to take the limit and let t go to negative infinity, and I'm going to replace the negative infinity with a t. Okay, that's all we're going to do there for right now. Now on this piece, I'm going to do the same thing. I'm going to do the limit and let t go to positive infinity, and I'm going to replace the infinity with a t. Okay, so now we just have to do the antiderivative, the fundamental theorem, and then evaluate the limit. So that's what you can do every time. So now, what is the antiderivative of 1 over 1 plus x squared. All right. Well, that is arctan. All right, that's arctan. And then over here, going to do the same thing. The limit as t goes to infinity. I've got to figure out the antiderivative of 1 over 1 plus x squared. That's arctan. And then I'm going to evaluate from 0 to t. So now I just got to do the fundamental theorem on both of these. Okay? I'm going to change my color because I'm getting tired of red. All right, so I'm going to do the fundamental theorem, and then I'm going to take my limit. So I'm going to do the limit as t goes to infinity. Got to do the fundamental theorem here. So I'm going to put a 0 in first. So that'll be arctan of 0 minus, and then put your t in, arctan of t. And we'll come back and fix that and figure it out. And then here I'm going to do the limit and let t go to infinity. Do the fundamental theorem. So I'm going to put t in first. So arctan of t minus, put in a 0, arctan of 0. Okay? All right, so now we got to figure out the answers for these. All right, so now we got to figure out what is the arctan of 0. I can actually get these two answers here. What is the arctan of 0? So that's meaning where on the unit circle does the tangent function have a 0 answer, is what that's saying. What radian measure on the unit circle gives me a 0 answer? And that is actually at 0. All right. Another way to think about it is I just memorize what arctan looks like, what the tangent function looks like. All right. So here's what the tangent function looks like. All right. So this is pi over 2, and this is negative pi over 2. This is what tangent looks like. Okay. So arctan means where is this guy 0? Well, this guy is 0 right here at 0. So the arctan is 0. Okay? All right, next. So now we got to think about the limit. So that means I'm just doing the limit of these guys. So what's the limit as t goes to infinity for negative arctan? I'm going to put an infinity here. So I'm looking at this picture again. Where is my tangent value? Infinity, arctan of infinity. That means what radian measure gives me an undefined value on the tangent curve. So if I'm looking at this picture right here, where am I going to infinity? We're going to infinity right here, so that's going to be at pi over 2. So this is giving me the answer, negative. Oops, I left off my negative, didn't I? Yes, I did. So I got that backwards. All right, sorry about that. So I'm doing the negative infinity, so I'm doing this side. So where is my t going to negative infinity? So where am I going to negative infinity? That's going to be negative pi over 2. So it's just the other side. All right, so then I was thinking about this one. So if t goes to infinity, this is the answer. We're over here, we're going to infinity, so that's going to be pi over 2. All right, so I left off that's why if you all were in here in class, you would help me out a lot. All right, so up here I had the limit as t went to negative infinity. I forgot to pull that down here. Y'all were probably screaming at me. Of course, I can't hear you. All right, but negative infinity here, negative infinity here. So we're looking at where is, if I plug in negative infinity into this arctan right here, we're thinking where is the tangent value going to negative infinity? Well, here is the tangent curve, and we only do the range from negative infinity, negative pi over 2 to positive pi over 2. So where is it going to negative infinity? Well, that's at negative pi over 2. So I'm doing the negative of negative pi over 2. And then over here, we're doing the limit of t going to infinity. So arctan of infinity means where on the tangent curve is my function going to infinity. So that would be at pi over 2. So now when I add these together, the negative of negative pi over 2 would be pi over 2 plus pi over 2, which is going to be 2 pi's over 2. So the answer is pi, which means this converges because I actually got an answer. All right, I actually got a numerical answer. So both of these last two converged because I was able to find a numerical answer. This last one was what, -1 or something like that? Yeah, -1. And this one was pi. So since I was able to actually calculate an answer, that means it converges to an answer. So each time you're doing these problems, you're always going to replace your infinity with a t and do a limit. and then you're going to do the antiderivative, the fundamental theorem, and then evaluate the limit by substituting in the t and figuring out the answers for each part. If you can actually get a numerical answer, then it converges. If you get infinity or negative infinity, then it diverges because your answer doesn't exist. All right, so this is the one that I wanted us to investigate just a little bit more. For what values of p is the integral convergent? Now, we did this one in problem number 1. All right, when we did problem number 1, we did 1 over x, so p was 1. And we found out that that one was divergent. So when p is 1, it's divergent. Okay, so now let's assume p is not 1, it's anything but 1. All right, so let's just do the process like we always normally would do. Let's just do the same thing. So we're going to replace our infinity with a t. So I'm going to do the limit and let t go to infinity, replace him with a t up there. And we're just going to do this just like normal, just having the letter p in there won't be a big deal. All right, so there's the first thing I did. So now we got to do the antiderivative, right? So we got to think of what is the antiderivative. I won't need my integral sign once I do my antiderivative. So what's the antiderivative? We're going to go from 1 to t. What's the antiderivative of 1 over x to the p? Well, think about 1 over x to the p. 1 over x to the p is the same thing as x to the negative p. So how do you find the antiderivative of x to the negative p? Where you're going to add 1, so that'd be x to the negative p plus 1. And then you're going to divide by your new power, which is negative p plus 1, right? Whenever you do an antiderivative, first of all, you bring your variable upstairs, change the sign of your exponent, and then to do the antiderivative, you add 1 and then divide by your new power. So that's what we would get for our antiderivative. So now we're going to do the fundamental theorem of that. Okay, so we're going to do the limit, let t go to infinity, going to do the fundamental theorem. So I'm going to plug a t in first. All right, now remember we're plugging a t in for x. Okay, we're plugging a t in for x, not the p. We're plugging a t in for x. So this is going to give us t to the negative p plus 1 over negative p plus 1. And then we're doing the fundamental theorem, so I put a t in first, then I'm going to subtract. Now we're putting a 1 in. Remember, we're replacing the x, not the p. So we put a 1 in there, so that'd be 1 to the negative p plus 1 over negative p plus 1. So there's my fundamental theorem. So now we just want to think about what happens. T is going to go to infinity. Okay, so this right here is going to be infinity to some power. So we just got to figure out what is happening here when p is either greater than 1 or negative 1 or under 1. Because we know that when p is equal to 1, we get divergence. So we're assuming p is anything but 1. So let's think what happens when p, I'll do the easier one first, when p is less than 1. So what's going to happen if p is less than 1? So let's pick a number less than 1. So let's pick 0, all right? So if you put a 0 up here, won't this be t to the first now? And when you put in infinity, that's going to give you infinity to the first power. So that's going to be d and e, right? And if we put 0 in over here, we're just going to have 1 to the 1 divided by 1. This is just going to be a number. So this part we don't have to worry about. This is just going to be a number over here. 1 to some power divided by whatever that's going to be. All right? So this is the part that's the issue. So if p is less than 1, so if p is a number smaller than 1, this is going to end up being a positive answer. So if I even make p negative 1, so say p is negative 1, that'll be the opposite of negative 1 plus 1, which is going to be 2, t squared. If you put infinity in here, infinity squared is still infinity. So if we do p less than 1, we're going to diverge because we're going to get d and e. All right, so think about what's going to happen now if we put in numbers greater than 1. All right, so let's see what happens when we put numbers greater than 1 in there. All right, think about a number greater than 1. Let's pick 3. All right, let's put a 3 in here. If I put a 3 in here, negative 3 plus 1 is going to be negative 2. So I'm going to have t to the negative 2, which where is that going to take my t? That's going to put my t in the denominator. And now I'm going to have t squared in the denominator. So when I put infinity in there, I'm going to have infinity squared in the denominator. So now I'm going to have a number divided by infinity squared, which is a really big number. So this is going to end up going to 0. And all I'm going to have is a non-numerical answer over here. So when p is greater than 1, this is going to actually converge and give me an answer. So we found when p was equal to 1, it was divergent. So that means down here on the divergent, I could put equals. So when p is less than or equal to 1, this expression is going to diverge. When p is greater than 1, it's going to converge. We're going to get an answer. All right. So if I put any number greater than 1, if I put a 4 in here, that'll make this -3, t to the -3, which means that's t cubed in the denominator, which is going to put me infinity in the denominator again, which is going to make this part 0. With this being -4 over here, I think that's what I was talking about, the number -4, then this gives me 1 to the -3, which is still 1, and then -4 times -p, now what did we say? I said -3, so that gave a -4, so that gave me t to the -4, gave me t to the -3, tossed it there. So if I put a -4 here, then or -3 here, that's going to give me 1 to the 4th power. And then down here, putting -3 is going to give me a 4. So I'm going to have 1/4. So I'm going to get a number every time, a numerical answer on this piece. What's happening over here is with the t, I'm putting in a negative number, which makes it positive. Or if I put in a number too big, bigger than 1, like a 4, I'm getting a negative answer here, which tosses this to the denominator. And so then that gives me infinity in the denominator, and it goes to 0. It takes a lot of thought and a lot of thinking about what is going on with the infinity. If my infinity is in the numerator, I'm diverging. If my infinity is in the denominator, then that means I'm taking a constant and dividing by a really big number, and that's going to go to 0. And so then only this piece is going to be my answer, which is going to be a numerical answer, and I'm converging. So you've got to really think about where your infinity is when you're doing these problems. And I know this is very confusing for the first time, so we'll keep doing more as we go. So actually, we've done this very first theorem here, and we're going to put this in on our back burner because this is going to come back to us later in another unit. But the integral from 1 to infinity of 1 over x raised to the p, that converges when p is greater than 1, but it diverges when p is less than or equal to 1. So the steps of these problems every time is just to replace the infinity with a t, and then do the limit. Then do your antiderivative, the fundamental theorem, and then evaluate the limit as t goes to either infinity or negative infinity, and just see if you can get an answer or whether you get an infinity divergent answer. So that's what this whole lesson's about. Now, your assignment is page 527, numbers 3 to 27 odd. I didn't give you very many because I just gave the odd ones. All right, so just start with number 3 and do the odd problems to 25.